I want to discuss the structure of stellar cusps around the galactic center. What sets the cusp? What is the stellar density profile we should expect? We're all familiar, I guess, with the Wolfe profile. So I'll try to say something which is related to that. And mostly I will try to understand what is the influence of the Hills mechanism, meaning the breaking of binaries, on the stellar distribution profile. I think it may be important. Related to that, so the second part of the talk, we'll talk about the way that stars actually approach to the black hole in the galactic center. Do they mostly do that by plunges, making something like a TDE? Or do they come as a nice, almost circular orbit spiral, which we call MRIs? What is the ratio between those two rates? I'll try to come up with an analytical solution for that, and then see what is the influence of breaking of binaries on that. Okay, so the setup we have is the usual setup. We have a black hole embedded in a sea of stars. There's some given velocity dispersion far away from the black hole, what we call outside the radius of influence. And the most important thing I'm going to say is that I'm going to neglect several effects, which may or may not be important. We'll leave them for some other time. All stars will have the same mass, so this may be a hypothetical problem. I don't know. I ignore resonant relaxation, which can accelerate especially the exchange of angular momentum between stars. And I'll assume that the galaxy has spherical symmetry, no special torques from triaxiality or anything like that. Okay, so it's interesting that all the names here are somehow related to Princeton. Peebles, right? Bacall and Wolfe. I was trying to dig out Wolfe. Maybe someone, the more senior guys, can help me. I think Bacall found Wolfe at Caltech. Do you know? Okay. I couldn't find too much about that. Okay, so anyway, when they tried, both these people tried to figure out the structure of the density of stars in the galactic center, exactly the problem I want to talk about, and they got to different conclusions. The first result was that of Peebles, and he predicted that the stellar density should go like r to the -9/4, while Bacall and Wolfe gave what is now acceptable profile of r to the -7/4. So let me try to explain how you get to both these results, and then we'll see what can we say about it, which is right. Okay, so if you say I have a black hole, and it's embedded in a sea of stars, and the stars are slowly drifting towards the black hole, and it's in a steady state, all of what I'm saying is going to be in steady state, then you expect that the flux of stars towards the black hole is a constant. So you can calculate what is the flux of stars. It's the number of stars at any given radius, or r cube, or is the stellar density, times the rate that it takes each star to have a significant deflection so it can be accreted towards the black hole. The rate is proportional to the density, to the cross-section, which is the distance for significant scattering square, and to the velocity by which the stars move. So you collect what you have here, which is radius dependence. This is rho twice, r cube, and v cube. If you're saying that you're dominated by the mass of the black hole, you know how v depends on r. So v goes like r to the -1/2, which adds to that cube to this thing. So if now we are saying that the flux of particle is constant, you will get that rho goes like r to the -9/4. This is the Peebles result. Okay. The easy way to think about the Bacall-Wolfe result is to say, no, but there is also exchange of energy. These stars, as they accrete towards the black hole, they also have to lose energy, and you need the energy flux to be constant. So you do the same calculation, but instead of the number of stars, you take the energy of those stars. So there is just E of r. E of r is gm black hole over r. So that gives you 1 power of r more in this expression. So this is this difference. And if you're saying this is constant, you will get the density goes like r to the -7/4, which is now the acceptable result. So what is wrong between those two? Both this should be constant and this should be constant. So how do we figure out what's going on? So the thing is the following. If you inject, suppose you had some mechanism that inject particles, stars, at some radius, at some given distance from the black hole. Let's say this is the injection radius. From there, they can either diffuse in or they can diffuse out. you should see what is the most limiting mechanism from these two, the energy flux and the particle flux. As they propagate inward, the energy becomes higher and higher. It becomes more difficult to shove them in energy-wise. So it's the energy criterion that is important. If you would be interested in what's going on when they're drifting outward, you would get that the energy becomes less and less important as you go out, and therefore it's the particle flux that is important. So I think, in fact, if you study this problem, which is a black hole and some ejection of stars at a given radius, a given distance from the black hole, you'll get both results. Inward of the injection points, you'll get the Wolfe result, and outward of the injection point, you'll get the Peebles result. Clear? Okay. This is a numerical simulation, some kind of numerical simulation, not real n-body simulation of this, done by Giacomo, a postdoc at the Hebrew University. And here he injects stars, let's say at 250 AU, and lets them diffuse by interaction with other stars self-consistently. And he gets these, indeed, two power laws. This is the Wolfe result. This is the Peebles result. This is stated here not in terms of density, but in terms of density times r cubed, the number of stars at any given radius. And this is fully consistent with the simple estimate that I've shown you before. Okay. If you're happy and you think you understood everything, so you can take a home exercise. And this is the following. If I inject stars in here, where do they go? Do they mostly go inward? Do they mostly go outward? And by what ratio? Okay, is it mostly equal? Or is it more in one direction? And by what factor? So you think about all I told you, and you should figure this out. More importantly, if this is also embedded in a sea of stars like we have in the galactic center, because most of the stars are not bound to the black hole, they don't obey this dynamics. And that gives you an external boundary condition in addition to this injection. Oh, I haven't told you the most important thing. What is this injection of stars that I'm talking about? I said that in the very beginning. I'm thinking of the breaking of S stars, of binary stars. So if you have a binary star on a very eccentric orbit, it comes close to the black hole. The tides from the black hole separate the binary. One of the stars is ejected maybe as a hypervelocity star, and the other one stays there as a bound orbit. So you have injected a star from a very large distance to a very small distance around the black hole. And then these stars can either propagate inward or outward according to these profiles. And this can be added on to the Wolfe profile that comes just from stars that are not binaries, that came from the radius of influence of the black hole. And that's the r to the minus 7 quarters.
Is the correction for ejection totally from close encounters negligible?
The correction, say that again. The injection is from breaking of a binary.
It's relaxation that is causing the diffusion.
Yes.
The relaxation can give some stars very high velocities and get ejected totally.
Oh, totally from the black hole? No, I haven't considered that. So the I think it's negligible. The relaxation, it's impossible, I think, even very close distances to the black hole, because there's no, it's possible?
Where it's possible, more stars get ejected than go into the black hole, but it doesn't affect the shape very much.
Okay. Well, if you go close enough to the black hole so that the orbital velocities around the black hole are bigger than the escape velocity from the stars, you won't have that mechanism. So close enough, you can't. Far enough, you can.
If I may interpret,
Yes.
possibly a question that may expose my ignorance utterly. So first of all, you need for this diffusion process, you need accretion of stars, right? You don't get it when you don't destroy the stars. Do you need that a priori?
You mean here?
No, that to build up a cusp that the stars.
So here I'm building the cusp from scratch. Suppose you have just a black hole, and someone is bringing a star from by hand at some distance from the black hole, again and again and again to this distance. And then you let them diffuse by two-body interactions only.
Okay. And the second question is, when you inject some at 250 AU, does the concept of a stellar density make sense at such a short distance from the black hole?
Yeah, why not?
There's just a few stars around. It's just very grainy. I'm not sure. 1
Okay.
second. That's like it's super tiny distance from the black hole. So I would not talk about density there anymore.
Well, It's up to you if you want to talk about density or not. There is a density. There is a density. You can look. No, it's more than a handful. It's a handful maybe of the bright stars that you can easily see. But solar mass stars, there are probably more. Yeah, so here this is the mass in units of 10 to the 6. The stars in the total number of stars, 4 times 10 to the 6. So yeah, roughly 100. So you want to say 100 is, you can make statistics on that or not? I can. Okay. So then you can also calculate the place. If you have some injection rate, which you can take from Scott's work, you and Tremaine, or whatever, or the rate in which binary break, and produce the stars at this radius, you can ask when does this distribution that is coming from the breakup of binaries connecting to the original distribution that has nothing to do with binary stars. And this comes to be at the fraction of stars which are binary times the radius of influence of the black hole. So you're affecting quite a big fraction because we think this eta is not a small number. Right? Maybe 10%, maybe more. Okay, so inward of 10% of the radius of influence, you should have this. Now, whether we see it in the data, I think not. Because the binary fraction determines the injection radius, the injection rate at this radius. The binary separation determines the injection radius, but the binary rate, the binary fraction, this tells you how many binaries you have to work with to create this. Well, that's, you know, in this calculation, it's an input. So it's whatever you want. You measure it, and you tell me what it is. If eta is small, you will not see this effect. If eta is large, you will see it. OK. OK, so now let's go back to the other questions that I was interested in. What happens when you add in gravitational waves? Because we know that MRIs are produced by stars going around the black hole and emitting gravitational waves. You can write down an expression for the time at which a star on a given eccentric orbit becomes less eccentric, or its semi-major axis reduces. So you can think of it in several ways. I remember that if you have two black holes at the same mass and they are touching each other, then in one orbit they merge. So this is the time to change the orbit. But if they have some mass ratio, it's longer by this factor. If you go out, they're not touching. It goes out by the distance to the 4. This is the periapse distance. If this orbit is circular, this is the distance to the 4. And if it's eccentric, then you have another power, which is the semi-major axis over the periapse to the 1/2. Now you can take the two-body relaxation time, which we already discussed. This is the time in which stars go close enough to each other in order to deflect. But I add another thing in here. If the orbit is very eccentric, I don't need a huge deflection. I just need a deflection strong enough to change the angular momentum by the amount that it is. So if the orbit is very eccentric, the angular momentum is very low. Rp, the periapse distance over R, the semi-major axis, is very low. So this becomes a small number, reducing the two-body relaxation time. I can compare these two timescales and get the place for which gravitational waves are more important than two-body dynamics, or gravitational waves are more or less important. So I put this all in this figure, which Yuri said is interesting. Where is Yuri? Yes? OK, so what do I see here in this figure? This is the semi-major axis of stars. This is their periapse distance. Okay? Periapse cannot be larger than semi-major axis. This is physically impossible. Okay? Or this upper part of the triangle. All our stars are somewhere here. This line is where the gravitational wave timescale is shorter or equal. T gravitational wave is equal to the two-body scattering timescale. So these two timescales are equal. So over here in this triangle, we're mostly affected by two-body scattering. Below this blue line, or whatever color it is, light blue line, it's mostly gravitational waves. Gravitational waves, they mostly make the orbit circular, and after it's circular, they shrink it. So this is what you see going here to the left. I remind you, this is periapse equal semi-major axis, so these are circular orbits. These are eccentric orbits. If it's under gravitational waves, it mostly become circular, and once circular, it will go down here. These are the MRIs. two-body scatterings mostly change, more easy for it to change the small angular momentum if a particle has an eccentric orbit. And therefore, particles here mostly go up and down. And if they hit a certain distance from the black hole, they become tidal disruption events. Okay? So if you ask yourself on this, I haven't put the binaries yet, but without binaries, where are MRIs coming from and where are TDEs coming from? Then TDEs can come along any of these lines until they hit this. Then it's a TDE. But if they started farther in, before they hit the line, they turn to the left because of gravitational waves, and these will be MRIs. So in this situation, all of these, everything that started on this line will become an MRI, and everything that started here will become a TDE. And now we know, if we take the Bacall-Wolfe profile, we know how many we have of each kind. So the source of most TDEs are from the radius of influence going down. The source of most MRIs is here, just at that boundary, a little bit inward of the boundary. The stars will go, hit that line, start feeling the gravitational waves, come here, and drop down as circular orbits. Okay, so that allows me to calculate the ratio between MRIs and TDEs very easily, because I know how many objects I have here, and I know how many objects I have here. I know the slope of this line. You can calculate for yourself, very interestingly. It's still surprising to me that this line always go through the Schwarzschild radius and the radius of influence, no matter what the parameters of the problem are. Okay? This line with the equality of gravitational waves and two-body interaction always go at RH and the Schwarzschild radius. And it has a slope of -½ So that tells you where this hits the tidal disruption radius, which depends on the size of the stars you're dealing with. That gives you that special point, inward of which you have MRIs, outward of which you have TDEs. And then you can calculate the ratio between the two, and it just comes to be the Schwarzschild radius divided by the tidal radius square. Super simple. Okay? So for solar mass stars, this is, I don't know, 7, 10. So we expect about 1% MRIs compared to TDEs. Okay. So now let's put the binaries in and see how they change the picture, because I have only 4 minutes. Skip this here. So same thing, now with binaries. So what happens to binaries? Suppose I have a binary in here, and it goes down to a more and more and more eccentric orbit. If it is a binary, it will break to the two pieces of the binary. It could merge as well. I ignore that in here. Okay? So if you want to take that, it's a correction to what I'm saying. The binary would break before the stars disrupt, because the binary is bigger than the individual stars. Where exactly it would break depends on the separation of the binary. But if it breaks, I know exactly where it goes. It goes to the periapse distance it has times the mass ratio between the star and the black hole to the 1/3. So a binary goes down this line, it breaks, then it goes to the periapse distance times 100, that's the apoapse. So no matter where it broke on this line, it always falls on this line. So this is the line of breaking binaries. Okay? And now you should look at this line and ask, from the survivors of the broken binary, where would you have TDEs and where would you have MRIs? So anywhere here, you would have TDEs, and anywhere here, you would have MRIs. So now you can calculate the ratio of these things again, and to an order of magnitude, maybe with a small number correction here, it's just the fraction of binaries. Because if I have the binaries spanning all separations equal in the logarithmic space, which is what we roughly think of binaries, I don't know how accurate is that, then I will have about the same number of binaries breaking at this distance as the number of binaries breaking at this distance coming into behind that R0 line, where they will be eventually dominated by gravitational waves. Okay? So that increases my ratio maybe by an order of magnitude to about 10%. So I think binaries are going to be important for that. The x's here are the S stars that we have orbits for. Okay? Just for comparison. In our idea, maybe they were born on this line. Some of them went up, by this diffusion in angular momentum. Some of them went down, made TDEs and MREs. Shall I go through this? What's my time? 2 minutes? OK. Let me tell you just a few words about extreme mass ratio in spirals. This is important maybe. So if the rates that I was talking about in the previous slides are correct, and they are higher than what we expected before, we may have a chance to have a star, a solar mass star, orbiting the black hole in the galactic center today. So we can see it maybe in gravitational waves, maybe in the Lisa band. Okay, it's reasonable. So you can ask yourself, how does the gravitational wave signal of this thing works? And it turns out that the way that the system reacts to a star going towards the black hole as an MRE, when it starts transferring mass to the black hole, the way the system evolves depends if the cooling time of the star, so-called the Kelvin-Helmholtz time, shorter or longer than the gravitational wave emission time. If it is shorter, then the star has enough time to adjust itself to its new mass. So as it evolves, it always stays on the main sequence, on its new main sequence mass. So its radius-mass relation is roughly linear. The radius is linear in mass, or the mass to the 0.7 as main sequence stars. But if its Kelvin-Helmholtz time is bigger than the gravitational wave time, it means you take mass out, and the star evolves adiabatically. So actually, as you remove mass from it, it becomes bigger. And it will go outward, away from the black hole, rather than inward. So that will give you a gravitational wave signal, which is an inverted chirp, which you can call a preach. Okay? So you will have preachers and chirpers in the system emitting gravitational waves in two different kinds. So the actual gravitational wave signal, this phenomena which is so global, depends on things which are opacities in the star, which will tell you what is the Kelvin-Helmholtz timescale. So this is pretty cool. OK, I'm out of time, so here is what I already told you. Forget the first one. Breakup of binaries can create the hypervelocity stars, but it also injects stars at some short distances from the black hole, and that can change the density profile around black hole. X binaries, I meant the component, the surviving component of the previously existing binary. So the bound component of that could be the source of most MREs, because they're being injected very close with a very small periapse distance, and with a small, here in this diagram, to the left of this line. So they can give you the needed MREs. And it creates a steeper cusp slope. And then I mentioned to you the gravitational wave signal, which can be both preach or chirp, depending on the ratio between these two timescales. I didn't tell you, but it's the low mass stars for which you expect preach. And it's the high mass stars, something like higher than 5 solar masses, for which you expect the normal chirp. Thank you.